Welcome to Spring LIB.
Hi, this problem uses the same setup from the previous problem, so let us draw it again. We have a rod here and we have a collar where a longer rod is attached with a pin. This point is D, and then actually this point is A. Sorry. Yeah, D is a point somewhere here on the rod where with a pin another rod is attached to this structure with a pin, and this point is D. This end of the rod is B, and then this point is E, and various distances are given. So from A to D the distance is 80 millimeter, and then the distance from D to E is 120 millimeter, and distance of A to D vertically is 150 millimeters, and distance from D to B 60 millimeters. Now it is given that at an instant where the angular velocity of dE is 2.4 radians clockwise, 2.4 radians per second clockwise, which means this dE, so E is fixed here, D can move with the other rod AB, so the velocity will be around this center, and it's given to be clockwise. So this is going to be our omega for dE. So it's given that omega dE is 2.4 radians per second. So then we are asked what is the velocity of end B and what is the velocity of the collar A, which is freely moving on this rod. So like any problem, again the basic principle is breaking the motion into translational and rotational part. So for dE, we know its angular velocity, so we can figure out the velocity of end D. So, and since it's fixed at this point at E, it can only make a rotational motion. It can't really make a translation motion because E is fixed. Because you remember, by the definition of a rigid body, all the points of a body, if it has a translational velocity, then it will share that translation velocity with all points. So it will have the same velocity. And since E is fixed, for dE, let me write it down. For dE, translational part is 0. So we draw the rotational part. So this is point E, which is fixed, and this is D, which is free to move, and the velocity is given to be, so it will be perpendicular, the velocity, angular velocity. So angular velocity cross R is your radial velocity. And remember, I repeat in all the lectures, but I just keep repeating, is that if your omega is clockwise, that means that the direction of omega is along minus k, it's going inside into the plane of the page. The radius vector is along E to D, and if you take the cross product of these two vectors, you will get the direction of radial velocity like this. So it's always perpendicular to the radius vector, and depending upon your rotation, you can intuitively figure out whether it's going to point up or down. So in this case, it's going to point up. Okay. And the magnitude is going to be omega r sine 90, because as I said, it's going to be perpendicular. So omega is 2.4 radians per second, and then length dE is 120 millimeter. So then velocity of point D is 2.4 times 120, which means 24 times 12. So 12 fours are 48, 12 twos are 36, plus 4, 408, and then units are millimeters per second because radian has no units. Okay, so now we figured out velocity of point D. But notice that this velocity at point D here is pointing perpendicular like this. So this is the motion which will give both point A and B some radial and some translational velocity. So let us assume that the angular velocity of rod AB is some omega. So then let's first write some translational velocity. So intuitively, if we push this rod D up, you can see that the A will actually move towards right. So so I'm just trying to decide what kind of rotational velocity we should give. So, sorry, what kind of translational velocity. So first let's talk about radial velocity actually, because that's easier to determine, because radial velocity is always perpendicular to the rod or the axis, perpendicular to the radius vector basically, not axis. So axis is here, it's vertically going inside the page, but the radius vector is along the rod. So the radial velocity here is going to point like this for point A, and for point B it's going to point like this. So it's clockwise. So D is going to move in this direction, and then A needs to move along the rod. So the components, you can see that this radial velocity of point A is going to have two components, one component along here, one component along here. And from this diagram, you can figure out what should be the translational velocity. So let me just write down the magnitudes here. So this is going to be omega times r AD, which is the distance between point A and point D. And this will be omega r dB. And the directions are as shown. So, and we also need the angles to figure out. So like in previous problem, if this is theta, this is also theta. So if we have some object pointing at 90 degrees, then this has to be 90 minus theta, because this is 90 and the sum of all the angles around a straight line have to be 180. So 90 plus theta, then in this has to be 90 minus theta. So this angle is 90 degree minus theta, and since this is 90, this is going to be theta. Okay. So now looking at this diagram, we can figure out what the translational velocity is going to be. Translational velocity has to be such that we know that the velocity of point A is going to point only along this vector, because it's restricted to move along this. So the other component has to cancel. So then it has to have some up component, which will be translational velocity. And by definition of rigid body, translational velocity is the same for all the points. So now we have broken the motion into translation and rotation. Let us just equate the relevant components and get our answer. So first of all, let's figure out sine theta and cos theta for this. So this we have done in the previous problem as well. So you can either refer to that, or let me just quickly do it anyways. So this is right angle triangle where base is 80, which is the distance of point A to point D, and then the height is 150, which is the vertical distance between point A to point D. And then this is our theta. So then simply tan theta is 15 over 8. And so you can draw a similar triangle with just 15 and 8. And then you also know the hypotenuse. So actually, yeah, rather than doing this in, rather than writing tan theta in the first place, let's just calculate the hypotenuse here and just write sine and cosine theta. So by Pythagoras theorem, this is going to be 150 squared plus 80 squared. And this is just 15 squared and 18 squared. 10 can be taken out common. So this is 10 times square root of 15 squared is 25 plus 8 squared is 64. So this gives us 10 times 225 plus 64 is 289, and square root of 289 is 17. So this is 170 millimeters. So then sine theta is going to be perpendicular by hypotenuse. This will be 15 over 17, and cos theta is going to be base over hypotenuse. This will be 80 over 17. Sorry, this is 150 over 170, 80 over 170. So these things cancel and we get 15 over 17, 8 over 17. Okay, now we are ready to equate the components because now we know the sine theta and cos theta. Okay, so right. So Vt has to equal omega RAD then this component, so cosine theta. So this will be actually, yeah, so, and this is a different omega. This omega is omega of AB, not of DE, which is given to us. So we'll just leave it as omega. Then RAD is the distance, is the length of the rod from D to A. So RAD is basically this distance. And we can see that this is like hypotenuse of that triangle. So RAD times cos theta will just give us the base of the triangle, which is going to be 80. So RAD times cos theta will just drop here. Then this will just be 80. So RAD cos theta is just going to be 80 millimeters. This is our Vt. This is equation 1. And then the second equation tells us that, so we should also figure out the velocity of point D because, yeah, so because this angular velocity is eventually coming from this D. So, and sorry, the translation velocity is coming from D. So Vt is same at all points. So at D also, Vt is going to point up. So this will be Vt. And we already know that at point D, so let us draw the diagram of point D separately. So at point D, because this is just for rod AB, so at point D, we already figured out that because of this rod, the angular velocity is perpendicular to rod DE. So this is going to point vertically like this. So if this was theta, this will be 90 degree minus theta. And so it's pointing up. So it's the same as Vt actually. So Vt from at point D, so at point D, this was at point A. So at point D, Vt just has to equal the velocity at point D, and velocity at point D, we have already figured out, is 408 millimeters per second. So this just gives us Vt is as 408 millimeters per second. So this implies that omega for rod AB, let's just call this omega AB, omega AB, omega AB. So omega AB, omega AB. Okay, all of them are omega AB now. So omega AB, this implies omega AB has to be 408 millimeters per second divided by 80 millimeters. So these numbers can be cancelled by 8 and the answer will be 8 5s are 40 and then 0.1. So 5.1 radians per second. Millimeters get cancelled. Okay. Now once we know omega AB, then we can figure out the velocity. So what is the velocity of point A? So velocity of point A, since A is constrained to move only in the right along the collar, that component will be this component. That will be omega AB RAD times cosine of 90 minus theta. So omega AB RAD cosine of 90 minus theta or sine of theta. You can interpret it anyways you like. This is 5.1 radians per second. And then RAD cosine theta we already know, but we also probably know sine theta. So let's look at this diagram again. So right, so this is our theta. Let me just delete this arrow. Yeah, oops, I probably deleted a bit more, so let me undo that. Can I undo it? Probably not, so I'll just redraw everything again. So from A to D to B we had this rod, and from D to E we had this rod. Okay, so this was our theta, and RAD is this distance. So what will be, this is hypotenuse, so what will be RAD sine theta? So RAD sine theta is just going to give us the perpendicular from the formula of sine theta. So RAD sine theta is just going to give us this distance. So it turns out that as we didn't really need to calculate these guys, because RAD only appeared as RAD sine theta, RAD cos theta, and RAD sine theta is just going to be this distance, which is going to be 150. But it's good practice to have these angles separately as well, because if the problem was more complicated. So anyways, so this is going to be RAD sine theta, which we just figured out that it's just the vertical distance. So this is 5.1 times 150 millimeters, and this was radians per second. So you multiply these guys, so VA is going to be 0 will shift, and 15 ones is 15, 15 5s are 75 plus 1 76, so 765 millimeters per second to the right, or this much I. So this is going to be the velocity of point A. Now velocity of point B, it's going to be a sum of these two vectors. So we figured out that VT is going to point up, and if this was our rod, then let's look at all the angles. So if this is point B, then from horizontal it makes an angle theta. So if this is the, so omega r was going to point in like this, so let's draw omega r here. So omega r is pointing like this. So if this is theta, this is 90, so this has to be 90 degree minus theta. So this angle is basically 90 degree minus theta. Okay, so from vertical, since it's 90 degree minus theta from horizontal, this angle is going to be theta. So basically, so at point B we have sum of two velocities. One is translational velocity and the other is rotational velocity, which is omega r dB, and then these velocities are at an angle theta. So this is going to be Vt times J plus omega r dB, and cos theta J, that will be the vertical component, plus the horizontal component is going to be negative because it's going to point towards left. So because if you break this velocity, one component will go here, another component will go here. Let me just write it cleanly. Omega r dB, not here. So omega r dB here. This vector gets broken into up and left. So left is going to be negative, so this is minus omega RdB sine theta I. So again, what is RdB sine theta and RdB cos theta? We look back at our diagram. So RdB is this distance in this right angle triangle. So RdB cos theta will give us this distance, which is not given, but the sine theta we know. Sine theta is going to be just the RdB, the perpendicular part, which is 60. So this distance is going to be RdB sine theta, and RdB sine theta is going to be 60. And RdB cos theta we can figure out from RdB sine theta. So let's actually, yeah, since the angle is same, then sine theta and cos theta are just going to be these numbers. So we don't need to worry about them. See, that's why it's useful to figure these out. Okay, so Vt we already know. Vt is 408 millimeters per second from here. And then J plus omega, these are all omega AB. So omega AB is here, so it's 5.1 radian per second. And then RdB sine theta, we know that RdB, so cos theta, yeah, let's just figure out RdB. So before putting all these numbers in, we know that RdB sine theta is going to be 60 millimeters. So RdB will be 60 millimeters times 1 over sine theta, which will be 17 over 15, because sine theta was 15 over 17 here. So 15 fours are 60, so this is 68 millimeters. Okay, so then our final expression for velocity of point B will be 408 millimeters per second, that's Vt in J direction, plus omega AB, that is 5.1 radian per second, cosine of theta, sorry, RdB, which is 68 millimeters, cosine of theta, that is 8 over 17, this also in J, and then minus omega AB, again 5.1 radian per second, RdB 68 millimeters, and sine theta, which is 15 over 17 times I. So 17 cancels 68 with 4, we get 408 millimeters per second J, plus 8 fours are 32, 32 times 5.1. So let's do 32 times 5, that is 5 twos are 10, and then 5 threes are 15, plus 1 16. So 160, and then 0.1 times 32 is just 3.2. So 160 plus 3.2, so 163.2 millimeters per second times J, minus, so this is 60. 60 times 5.1 will be 6 times 51, so 6 ones are 6, 6 fives are 30 millimeter per second I. So finally we get minus 306 millimeters per second I, plus we can sum these two numbers. So 400 plus 100 is 500, 63 plus 8 is 71, so 571.2 millimeters per second J. So this gives us velocity of point B as well. So all the problems in this chapter are basically break the motion into translation plus rotation, and then equate the components based on the constraints and the specific problem, and eventually you are able to solve for each of the components. So remember this, and just some basic geometry, and be patient to find out all the angles. Should be able to figure out everything. See you in the next problem.